All right, so last time we were talking about NMR, and we were talking about proton NMR. Today we're going to talk about carbon NMR, and then move into chapter 12 and try to get as far through that as we can. But I want to do a little bit of a review. So let's try to predict what the NMR for this molecule that I've drawn up here on the board might look like. Approximately. We don't have to be extremely accurate with it. Okay? How would I name that molecule? Bromo, propane. Do I need a number? I do need a number. It's one bromopropane because I can also have two bromopropane, right? So we're gonna actually look at one bromopropane, and we're gonna look at two bromopropane, and we're going to see what the differences in those spectra might look like. Okay, so let's focus on the one bromopropane first. How many signals would you expect to see for one bromopropane? Proton signals. How many unique signals will we see? Not splits, but just signals. We should see 3, right? We've got this carbon that has 2 hydrogens attached to it that's attached right to the bromine. We have this carbon that has 2 hydrogens that is attached to 2 other carbons, so it's clearly different than this one. And then we have the CH3 on the end, which is only attached to that CH2. So right, we would expect to see 3 proton NMR signals for this particular compound. All right? Now, for 2 bromopropane, I think you all will agree, these are just isomers of one another. They have the same molecular formula, same number of carbons, same number of bromine, same number of hydrogens. How many signals would I expect to see for 2 bromopropane? 2, right? I see clearly that there's a mirror plane here, which makes this methyl group and that methyl group identical. So I would expect to see a signal for this hydrogen and a signal for the methyl group. And since they're equivalent, it would appear as one signal. So here we're going to have 2 proton NMR signals. Okay? Very good. So now let's see if we can't come up with what the NMR, the proton NMR spectrum might look like. So here's my chemical shift, here's my intensity on the y-axis. Okay? And we know that we're going to go from about 0 to 10, or 10 to 12 or whatever is about the range, right? And we know that 5 is kind of a magical number. Where am I going to see the signals? To the right of 5 or to the left of 5? Am I going to see signals between 0 and 5 or between 5 and 10? Yeah, between 0 and 5. Because every carbon is sp3 hybridized, right? We're going to see stuff in the sp3 hybridized region. So where would you start? I'm going to start on the right looking at this just because it's on the bromine, right? Or bromine's attached to it. I've got 2 hydrogens that we've agreed will give a signal. What will that signal look like? Where will it be? Closer to 5 or closer to 0? Closer to 5. So let's just pick somewhere over here. So I'm going to see my signal somewhere in here, right? And what's that signal going to look like? Is it going to be a single line? Okay, it's going to have 3 lines. We call that a what? That's going to be a triplet, right? And it's going to have a shape that looks something kind of like this, right? And it's going to integrate for what? What's the integral going to be? What's the integral tell me? 2. Yeah. What is it telling me? Why is it 2? Not neighboring, but the integral tells us how many protons give rise to that signal, right? So it's going to give me an integration of 2, right? So I'm just going to write 2 above it. I'm not going to draw the little line because I don't have a ruler to kind of make it. Okay, now let's go over to this one. Where's this one going to be? Over here or over here? Where's it going to be? Gonna be on the other side of it, or is it gonna be here, here? Where do you think?
Closer to 0?
Closer to 0. Is it gonna be really close or kind of intermediate?
Intermediate.
Yeah, kind of intermediate, right? It's not attached to the carbon with the bromine, but it's certainly closer to the bromine than this one, right? So yeah, it's gonna be somewhere over, let's just put it right in here. I'm not worried about the exact shift, right? It's got 2 protons, so the integral is gonna be 2 as well. But how many splits are we gonna have?
Is it gonna be 5?
Pardon?
Is it gonna be 5?
Okay, so how many neighbors does it have?
Okay.
It's got 5 neighbors, so how many splits is that? 6. It's n plus 1, right? So we're gonna have 6 peaks, and it's gonna be somewhere around here, so we have 1, 2, well, I'm drawing it not to good scale here. 1, 2, 3, 4, 5, something like that. Trust me, I think I drew 6. Okay, and now we've got this one left, right? And where's it gonna be? Is it gonna be somewhere in here, somewhere over here? Is it gonna be closer to 0? It's gonna be closer to 0. It's gonna be around 1-ish, right? And it's got 3 protons, right? So it's gonna have an integral of 3. What's its shape gonna be? How many splits is it gonna have? How many neighbors does it have?
It'll be a triplet.
Be a triplet. It's got 2 neighbors, right? So it's going to appear as a triplet. It's going to integrate to 3, so it should actually be a little taller, but I'm not drawing all this to scale. So that's what we would expect the NMR to look like for 1 bromopropane. For 2 bromopropane, again, we're going to draw this out. I've got chemical shift, I've got intensity, there's 0, there's 10, there's 5 in the middle, right? Everything's going to appear on this side of 5 still, right? Everything's sp3 hybridized. We've said we're going to only have 2 signals, right? So here I've got a proton on the carbon with the bromine. So it's going to appear pretty far down again, right? So it's going to be somewhere in here. And it's got how many neighbors? This one proton has 3 neighbors here, 3 neighboring protons here, and how many here? 3. So it's got 3 neighbors, so what's the peak shape going to be? What's the splittings? What's the rule? N plus 1. So if it's got 6 neighbors, it's going to appear as 7, right? So I'm going to draw this 1, 2, 3, 4, 5, 6. Who knows 7, right? Whatever it looks like. A lot of peaks, right? And now we're going to have one other signal. Where's this signal going to be? Is it going to be close to 0 like this one, or is there going to be a little more out here? What do you think?
It's gonna be a little bit more towards the middle.
It's going to be a little more towards the middle. Very good, right? And we've got, so this one integrated to 1, right? This one has 6, so it's going to integrate to 6, so the peak area is going to be a lot bigger, right? And what's the shape of this signal going to be? How many neighbors does that CH3 have?
Do you only count the 1?
You only count the 1. So it's going to be what? It's going to be 2, we'll call it a doublet, right? So somewhere right around in here I'm going to have, I can draw a doublet really well, right? So, and that's going to integrate to 6 protons. Okay. So, isomers of one another, very different spectra. If you were to try to figure this out by IR, you wouldn't have been able to distinguish one from the other very easily. And everything would have been in the fingerprint region. But NMR gives me the ability to actually go in and determine structure a lot easier. Okay. Does that make sense to everybody? You will have to do something like this on the exam. You won't be drawing out the spectra, right? But you will be given, there's a couple ways I can do it. I can give you the molecules and ask you to tell me how many signals do you expect. I can give you a spectrum and ask you which of the following molecules is most likely that. results in that spectrum. So those are the types of things that you'll need to be doing. Notice in all of these cases, we're only looking at the hydrogens because this is proton NMR. Okay? Doesn't say anything about the carbons, right? We've assumed that the carbons are there given that I drew the structures, right? But fortunately for us, we can also do NMR experiments on carbon. And it turns out, if you'll remember from last time, I told you that as long as an atom has either an odd mass number or an odd atomic number, its nucleus spins. Why that's the case, I'm really not sure. That's a question for the physicists. Okay? But if something has an odd mass number or an odd atomic number, its nucleus spins, and so it gives rise to NMR spectra. You know, for the years that I've been using this slide, this came from the publisher, that is not age 11, it should just be 1, right? Proton. Number 1, not 11. So carbon-13 has an odd mass number. And so carbon-13 does give rise to NMR. So you all probably know that there are 3 common isotopes of carbon. There's carbon-12, which is the most abundant. There's carbon-13, which is almost all of the rest of it. And then there's a little tiny bit of carbon-14. And carbon-14 is radioactive. So when you hear carbon dating, they're talking about carbon-14. Okay? That gets generated in our atmosphere through a nuclear reaction, believe it or not, between the sun's particles and nitrogen in the atmosphere. And so that's how plants uptake carbon-14, and you do all that stuff. But carbon-13 is naturally abundant to only about 1%. Proton is naturally abundant to over 99%. You can go run a proton NMR in like 5 minutes. Most of your time is just sitting there getting the computer set up to run the experiment. Carbon-13 takes longer because there's not as much carbon-13 in nature. Okay, so it's more dilute, if you will. And so when my students go up and run carbon-13 NMRs, it almost always it takes at least 30 minutes to an hour to run a good carbon-13. Okay, almost always. Okay, so but we have carbon-13. We can look at the carbon signals. Okay, and just like proton, we're going to have the chemical shift on the x-axis, and we're going to have intensity on the y-axis. And this is a chart that you'll have from the slides. Okay, what's different with this scale compared to proton? It's in hundreds, that's right, not in tens, right? So it turns out that a carbon spectrum goes somewhere between 0 and 200 in terms of chemical shift. Where do you think we're going to draw the line? Where would you draw the line?
About 70.
Okay, yeah, that's not too bad. Turns out I'd say let's just draw it at 100. Okay, we split it in half. And what you'll see is everything on the right is going to be things like alkanes, sp3 hybridized stuff, and sp hybridized stuff, just like we saw in proton NMR. And to the left are going to be everything that has carbon that's sp2 hybridized. So alkenes, aromatic rings, carboxylic acids, esters, amides, aldehydes, and ketones. Okay? You're going to see the signals being in kind of these places. What's nice about having such a broad scale? What do you think? Huh?
It's easier to identify.
Yeah, it's usually, things aren't as crowded. It's easier to identify your signals. Proton NMR, sometimes things get really close. And it can be hard to figure out what's what sometimes, especially if you're talking about a really big molecule. But with carbon-13, given that the signals have a large frequency range, you can usually clearly see the different signals pretty easily. Okay? So yeah, that's kind of what we're dealing with right there. All right. Your book has a table of chemical shifts. This isn't the table that's in your book. This is just the table that I like. But you can kind of see where you can expect those different shifts to be. And so we're not going to spend too much time talking about this. You all can look at tables. I know you know how to read a table. So, you know, if you're trying to figure out if something in an alkene or an aldehyde, I mean, you can clearly see there's different chemical shifts for those carbons. You'll be able to figure those out pretty easily, okay? So, let's look at some examples. Here's an example of a carbon NMR spectrum. What you see at the top, Q, T, D, D, S, S, isn't always going to be there. It turns out that carbon-13, only being 1%, what do you think the odds of two carbon-13s being bound together in a molecule? Is the probability high or low?
No.
It's very low, and so carbon-13 doesn't split carbon-13. But protons will split carbon-13. So the hydrogens that are attached to the carbon-13 will split it. So if you have 3 hydrogens attached to a carbon, that carbon signal will be split into a quartet. The problem with that is that when you start splitting carbons, they start to overlap each other and it starts to look like a forest of trees as opposed to signals. So it turns out that the physicists figured out how you can decouple the protons. And so what does all those look like? They all look like singlets, don't they? A carbon NMR, especially for the purposes of this class, are always going to be single peaks. And each peak represents a unique carbon. Okay? What you're seeing above, Q, T, D, D, S, S, that Q means that if it were not decoupled, it would appear as a quartet. So if it appears as a quartet, what does that tell you? How many hydrogens has to be attached to that carbon? 3, because it's N plus 1, right? If it's a doublet, that means there's 1 hydrogen attached to it. If it's a singlet, that means there's 0 hydrogens attached to it. All right, so with this information in hand, the charts that I just gave you, get in your groups and try to figure out what that spectrum is. It's the same as before. You're going to try to figure out the number of signals first.
Can we review those charts one more time?
Sure. This one's probably going to be the easier one for you to use. You got it? All right. Try to solve that problem. First thing you want to do is ask yourself, how many unique carbon signals would you expect? Not proton signals, carbon signals. Eliminate those. How many signals do we see in that NMR spectrum? Pardon? 6. There are 6 unique signals. So the first thing I'm going to do on my exam is I'm going to look and ask myself, can any of those be eliminated based on that? So I look at this molecule, oh, dang it. I look at A, right? And I see a mirror plane that runs through here. right? And so I can count the carbon. So I'm going to have 1, 2, 3, 4, 5, 6 unique carbon signals. So that one could be it, right? I look at B. Again, a plane that runs through here. So 1, 2, 3, 4, 5, 6, 7. Can it be B? It cannot be B. So we're going to eliminate B. C. Again, a plane that runs through here. 1, 2, 3, 4, 5, 6. That's possible, right? And then D. Again, there's a plane that runs through here. 1, 2, 3, 4, 5, 6, 7. So I can eliminate which ones? I can eliminate B and I can eliminate D. So that leaves me with A and C. You just went from a 1 and 4 gas to a 1 and 2. Time to put the money on the table, right? We're in good shape there. And all we had to do was count lines. Okay? So, what do you think the right answer is? How many are in Camp A? Oh, come on, be brave. How many are in Camp A? How many are in Camp C? I'm assuming the rest of you are undecided, waiting to hear what I have to say, right? All right, well, let's think about it. If I look at A, I would expect this CH3, right? It's attached, this carbon's attached to an oxygen. I would expect it to be a little closer to 100 than 0, okay? And it's got 3 hydrogens attached to it, so that carbon would actually be a quartet. And I see something there that's kind of that way. I would expect this carbon with its 2 hydrogens to be in, pretty closely with this one because it's got an oxygen attached to it, and it would be a triplet because it's got 2 hydrogens, and so I see that, and that makes sense. I would expect for this carbon and this carbon, since there's no hydrogens attached to them, to be singlets, and it's going to be in the aromatic region. That would be something like this. And then these carbons, since they have 1 hydrogen attached to them, I would expect those to be doublets, and that's what I see there. So that seems to align with the spectrum. Now, if I look at this one, right, I would expect to see a quartet and a triplet, which I see quartets and triplets, but these aren't attached to anything like oxygen. So I would expect these to appear maybe closer in here somewhere. I would expect this to be a singlet, and I have a singlet somewhere. And here I have a hydrogen on this one, so this carbon should be a doublet. And I don't see any doublets over here, okay, in this region. But here I have a doublet and a doublet, which I might expect. So it doesn't seem to align very well with C. And so the correct answer here is A. So if you were in Team A, you are correct. Okay? All right, here's another example. Now I'm giving you a carbon NMR, a proton NMR, and 4 choices of compounds. So now you're going to start to put together multiple types of spectra to see what you can come up with. And what you'll see here, you see this little peak that's labeled CdCl3 at around 77? That is the solvent that they dissolved this compound in. So ignore this, okay? So ignore that. Take a couple of minutes, work with your partners. And on the proton NMR, what you're seeing up there, 3H, 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 or 2H, 2H, that is the integration. All right, folks. How do we go about doing this? Well, let's make it easy on ourselves, right? Where would you start? Pardon? Okay, you can count the number of signals. How many signals do we see in the carbon NMR? Yeah, I count 5, right? There's 1, 2, 3, 4, and 5. Again, we ignore this one, right? Okay, so that's a good place to start. I also know that I'm going to draw a line at 100, right? And all this is going to be either SP or SP3 hybridized, and all this is going to be SP2 hybridized. I noticed I have one signal that's SP2 hybridized. Can I eliminate anything based on that information? Okay, what can I eliminate?
Esters, acids, and.
Well, that's what it could be. What could I eliminate? Right, if this is SP2 hybridized, right? Is there anything up there on the list that's not SP2 hybridized? D. Yeah, D doesn't have anything that's SP2 hybridized. D goes away. Right? Now what Alyssa was talking about is out here around 210 or so, we're going to be thinking about aldehydes and ketones. We might want to go to our chart. Right? So we're going to go to our chart. Right? And we see that esters, acids, and amides are going to be around 160. And aldehydes and ketones are going to be somewhere around 200. And our peak is where? Around 200. So what can I eliminate based on that? It can't be an ester, right? What's an ester? A is an ester, B is a ketone, and C is an ester. So what can I eliminate now? I can eliminate A and C. So if I've eliminated D, A, and C, that means the answer has to be B. That's right. Did I have to go through and interpret every piece of this? I did not. As a chemist, would I have done that? Yes. You're not chemists. Okay? I don't expect you to, but you're using the spectral information to make choices. And when you stop and look at it, now everything makes sense. Right? That should be a singlet, and we see a singlet for 3 hydrogens. That should be a triplet because it's got 2 neighbors, right? And it should be pretty close to this one, and that's what we see. That one should be 6 peaks, 2 protons, around 1.5, and then that one should be the closest to 0 at 1, and that should be a triplet. So all that adds up. When you look at the carbon, all that adds up, and that's the only one that really makes sense. So you could have gone through and done a complete analysis of both spectra, or you could have used process of elimination like we just did to figure out what couldn't possibly be the case. Any questions about that? Okay. This is like lifting weights, folks. You don't get good at it by reading about it in a magazine, you know? You get good at it because you do it. And you're going to have some examples in your homework that are pretty challenging, and that's okay. But again, try to use your process of elimination as best you can. Use your charts, use your protons and carbon NMR signals, use your IR spectra to try to figure out what the structures might well be, okay? So that is NMR spectroscopy in a nutshell. And again, there are multiple classes that you can take on NMR. It's a very useful technique. And we just covered the very, very top piece, or the surface of NMR. All right. So, as we get into chapter 12, we're going to start talking about aldehydes and ketones. We're going to talk about some of their properties, and we're going to talk about some of their spectra. Okay? We've already started talking a little bit about their spectra. But before we get into anything, I want you to remind me, what is an aldehyde? How would I draw out the aldehyde functional group? going back to chapter 2, I think. All right, what was an aldehyde? Tell me what I need to draw. There is no OH. That would be an alcohol. Or carboxylic acid. There is oxygen, but it's not an alcohol.
Carbon group bond with hydrogen.
Okay, so a C double bond O, that's a carbonyl with a hydrogen attached to it. What has to be attached on the other side? Just anything, right? So we're just going to put R, what has any carbon. That is an aldehyde. Okay? What is a ketone? That's right. So a ketone is still a carbonyl, but instead of having hydrogen attached, it's got two other carbons. Now they can be the same, they can be different. Okay? So aldehydes versus ketones. Okay? So some common aldehydes that you all are already familiar with that we've already talked about, and ketones. So we've talked about acetone before. I told you that that was the main component of fingernail polish remover, paint thinner. And then common aldehydes would be something like acetaldehyde, which we learned in a previous chapter, your liver makes when it oxidizes alcohols. So you go and you drink your favorite beer, your liver actually oxidizes that to acetaldehyde. You drink too much beer, you get too much acetaldehyde in your bloodstream, that's what causes the hangover, okay? And so these are some simple examples of aldehydes and ketones. All right. So, aldehydes and ketones have a particular type of reactivity. They like to react with nucleophiles. And it turns out that aldehydes are more reactive than ketones towards this nucleophilic addition. We've talked about nucleophiles before. What were we talking about when we talked about nucleophiles before? What were the reaction mechanisms we learned about? Substitution reactions, and those were SN1 and SN2. We learned about those. Nucleophiles will also react with carbonyls, okay? And it turns out that aldehydes are more reactive than ketones. And for the purposes of this class, it has to do with the fact that an aldehyde is less cluttered than a ketone, right? So ketones have more steric hindrance. There's more stuff in the way for the nucleophile to have to get around to do the chemistry. Having said that, both of them are quite reactive towards nucleophiles, okay? Some of the physical properties that you'll see with aldehydes and ketones. So here we've got an example of looking at both, right? You'll see that aldehydes are going to be somewhere between, in terms of boiling point, somewhere between your alkane and your alcohol. The aldehydes and ketones can form van der Waals interactions. They can form dipole-dipole interactions, but they can't form hydrogen bonds with each other because there's not a hydrogen on the oxygen. Now they can hydrogen bond with water, but we're talking about pure substances here, so they can't hydrogen bond like alcohols can. So you'll see that the difference in boiling point there, right? So if you go from the alkane that boils around 36 degrees, the aldehyde and the ketone going to be around 78, 80 degrees if you average those two, and then the alcohols, which are well over 100 degrees, okay? You're going to find that the solubility of aldehydes and ketones, they're going to be soluble in organic solvents. You're going to be able to take an aldehyde or a ketone, you're going to be able to dissolve it in things like dichloromethane, methyl acetate, and benzene, and other organic solvents. You'll be able to do that, okay? And aldehydes and ketones follow our 5-carbon rule. Okay, so if there is 5 or fewer carbons for every aldehyde or ketone function group, it'll be soluble in water. Acetone, soluble in water. Take your nail polish off, you don't worry about trying to rinse it off in the sink because it's water soluble. It goes down, right? It's got 3 carbons, 1 ketone, it should be soluble in water. Acetaldehyde, 2 carbons, 1 oxygen, It's soluble in water. It can stain the bloodstream, right? That's how the acetaldehyde, when you overindulge, gets to your brain, right? It's water soluble, okay? Start to add more carbons, that solubility starts to go down as you might expect, okay? Both of these have a C double bond O, so in the IR spectrum, we're going to expect to see that carbonyl stretch between what and what? Where do we start in IR? What's the number? 1,500. So between 1,500 and what? 2,000. We expect to see a nice, strong absorption, right? So this is an example of propanol. And in fact, we see a nice, strong absorption, right? See it very nicely, okay? You can also expect to see the different types of hydrogens. But an aldehyde or a ketone, you're going to see something between 1,500 and 2,000. It's very, very strong. And in this case, it occurs around 1739 wave numbers. Okay? All right. NMR spectra, pretty straightforward. Okay? You're going to see that the sp2 hybridized carbons are going to be where you would expect to see them. Where would that be in the carbon NMR? Aldehydes and ketones, where would you expect to see that? In the carbon? It's up there, right? Around 200, right? If we're just roughly talking about it. The hydrogen on the aldehyde is going to be pretty far downfield in the proton NMR. You're going to find it somewhere around 9 to 10. Okay, so I would expect this proton to be somewhere around 9 to 10. That's usually a good indication that you've got an aldehyde. Obviously, a ketone not having a hydrogen on that carbonyl carbon isn't going to have anything down there. Okay? You're going to find that the alpha carbon of a carbonyl is going to be around 2.5. That alpha carbon is the carbon right next that's directly attached to the carbonyl. It's not going to be closer to 1 or 0. It's going to be around 2.5. So it's going to kind of be in between that 0 and 5 mark that we think about in the proton NMR, okay? And then we've already talked about the carbon, okay? So here's an example of a proton NMR spectrum for propanol, okay? HA, does it make sense that where HA is? There's HA, there's HA, right? Does it make sense that it's appearing right there at 1? Why? It's the furthest away from the carbonyl, so it's least electronegative, that's true, right? What about its shape? Does the splitting make sense? What is that? That's a triplet, which means it has how many neighbors? 2 neighbors, that makes sense, right? HB, does that make sense? HB is around 2.5. That's the alpha carbon. That's exactly where we thought we would find it, right? Those hydrogens should be around 2.5. But does the splitting make sense? Does it? How many neighbors does it really have? You're right, it's got 3 neighbors here, but remember, neighbors are on the, so if these are the protons I'm looking at, I look at the connected carbon and ask myself, right, so there's 3 there, right? But here's a carbon that's connected to it too. How many does it have? 1, so it really has 4 neighbors, right? But it's only appearing as 4 peaks. Why do you suppose that is? It's similar to that. It has to do with the fact that this is an sp2 hybridized carbon and this is an sp3 hybridized carbon. And it turns out that this actually is coupling to this, but the coupling constant is so small that you can't see it. Okay? So it looks like a quartet. Okay, so that can throw some people off sometimes. Because you would also expect HC, since it's got 2 neighbors, to appear as a what? You would expect it to appear as a triplet. And sometimes you can see it, but the triplet, the peaks are so close together that they look like a singlet. You really have to blow in really close sometimes to see it, okay? So that is one of the tricky things about aldehydes, is that that hydrogen on the aldehyde doesn't give rise to really strong coupling. So sometimes you don't see the splitting like you might predict. So don't let that throw you for a loop, okay? The carbon spectrum, very easy, right? We've got these two carbons that are going to be over here, right? A should be closer to 0 than B, and that's what we see. And then we see this carbon peak around, what is that, 205 or something? And that's for that carbon of the carbonyl. Yeah, that's where we find that. All right? All right. I want you to take a look at those two spectra, and I want you all to give me kind of your analysis of what is what. Now, these are real spectra, and it turns out that I didn't blow these up very good, but you can kind of see that there's something going on here with this peak, okay? So which one belongs to which? Which spectra belongs to which molecule? This is a situation in these molecules where you have a lot of similar signals and they all kind of start getting jumbled up together. And so you can really start to make a difference here by looking just at the aldehyde signal. Okay? Now I told you previously that it's sometimes hard to see the splitting, but in this particular case we can see it quite well. What's this split into? That's a doublet, and what do you think this one looks like? That's a triplet. So if I look at the aldehydes, right, this hydrogen has how many neighbors? How many hydrogens are on this carbon? 2. So I would expect this to be the triplet. This one only has 1 neighbor, so I'd expect it to be the doublet. Yeah. And so this molecule actually belongs to this spectrum. This molecule belongs to this spectrum. Now you can go through and you can actually look at the other signals and you can quite readily figure out what it is. So for example, this single peak here, or not, it's not a single, but this peak that's split into many things is actually this one. That's 1 hydrogen, but it's got 6 neighbors. And so you see the complicated thing, but you don't have to go through and do the entire interpretation to figure all that out. All right, let's talk about some interesting aldehydes and ketones, more than what we've already talked about. Citral comes from lemongrass. This is that lemony odor. If you like lemony smelling things like your car freshener or your Glade plug-in, whatever you've got, okay, if you like that lemony smell or the lemony furniture polish, they put citral in it to give it that odor, okay? What's kind of unique about this? How many other functional groups are there? There's the aldehyde. Are there other functional groups? We've got the alkenes, right? So this is an example of a molecule that has both the alkene functional group and the aldehyde functional group. How many carbon signals would you expect to see for citral? Is there any symmetry that's going to make one side equal to the other? No, not really, right? So I'm going to see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 unique carbon signals for citral. Cinnamaldehyde. This is the odor of cinnamon. If you like that cinnamon smell, this is what they're putting in your car freshener. If you've got a cinnamon aroma car freshener, this is what they put in there. It's an aldehyde. It's very volatile. It smells nice. You can actually extract this from cinnamon sticks. Used to be a lab we used to have students do. Take cinnamon sticks, put them in water, you boil the water, and out comes the water, and it carries the cinnamaldehyde with it. It's the odor of cinnamon. Benzaldehyde. It's a benzene ring attached to an aldehyde group, right? So benzaldehyde, this is a very common small molecule aldehyde that we use in labs all the time. Yes?
Is that why people like perceive amaretto as tasting like cherries? It's made from almonds.
Yeah, I would think so. Yeah, and benzaldehyde. I think if you go up to the lab and if I opened a bottle of benzaldehyde, I think you would most likely associate it with the like maraschino cherry smell as opposed to an almond smell. I've never really gotten when I try to smell almonds. Unless you crush them and get the oils, I don't think you really sense that benzaldehyde smell. But the cherries, you really get it. And if you open up a bottle of benzaldehyde, it's like somebody opened up a jar of cherries. It really does smell quite pleasant, actually. And then this is 2-heptanone. This is not a aldehyde, it's a ketone. If you like blue cheese dressing, if you like blue cheese for anything, this is what's giving you that odor. It's that ketone. You didn't have a nice look on your face about blue cheese. Not a blue cheese fan? No? Don't like blue cheese dressing? No? Nothing blue cheese, huh? I like blue cheese. And 2-heptanone is what is responsible for that odor. Okay? Okay. What is important about the chemistry of carbonyls, if you think about the C double bond O, there are two types of bonds there. What types of bonds are they? We have a sigma bond, and then we have a pi bond. And which one is the weaker bond? The pi bond. That's good, right? You all know that pi bonds are weaker. Okay? That pi bond can function kind of like a leaving group. So a nucleophile can attack the carbon of the carbonyl, break that weak pi bond, and put those electrons on the oxygen atom. So you can almost think of this as the electrons being the leaving group. That's not technically correct, but you can think of it that way. Okay? You're breaking the weak pi bond. And in breaking the weak pi bond, we're forming a strong what? A strong sigma bond. So I have more sigma bonds in the product than in the starting material, right? And so you might predict that you would form more of the product than the reactant. But here is an example of where the equilibrium actually lies to the left, not the right. It has to do, you have to compare the bases. Okay, so this nucleophile, chloride, is a weak base, whereas the alkoxide is a stronger base. Equilibrium never favors the stronger base. It always favors the weaker base. Okay? So even though we're generating more sigma bonds, you're generating a stronger base. So the equilibrium is actually going to lie to the left in this one. Okay? Now, if this was a strong base and this was a weaker base, it would favor the other way. Okay? So you got to kind of keep that in mind. Okay. So, this brings us to nucleophiles that are actually capable of favoring the product. I told you that there's a lot of names that get thrown around in organic chemistry, and I've tried to shield you from some of them. Right, we talked about Williamson ether synthesis before. I told you that we use a lot of people's names in organic chemistry. This is one name you're going to have to know. It is the Grignard reagent. Grignard. Victor Grignard, back in the early 1900s, discovered these and went on to win a Nobel Prize for their discovery. If it won a Nobel Prize, do you think it's important? Yeah, it's real important. We use Grignard reagents all the time today. They are great nucleophiles. Okay? They are great nucleophiles. They will add to carbonyls 100%. These reactions go to completion. So that must mean that a Grignard reagent is a strong or a weak base. If it's adding to a carbonyl and it's going to completion, does that mean that the Grignard reagent is strong base or a weak base?
Strong base.
Very strong base. So these are really strong bases. They have pKa's of around, around 35 or 40, somewhere in that ballpark. Remember, alcohols have pKa's around 16, 17, 18. So the Grignard reagent is much more of a base than is the alkoxide that you get, okay? And again, Victor Grignard was awarded the Nobel Prize for these. I guess it was in 1912. And they all have the general formula. What did I do with it? It's in my back pocket. Thank you. They all have the general formula of RMGX. The Mg is important here. What is Mg on the periodic table? Magnesium. This has a carbon-metal bond. These are called organometallic reagents. This is kind of cool. We're no longer talking about carbon being bound to carbon. We're talking about carbon being bound to a metal. Are metals electronegative or electropositive? Do they like to give up their electrons or do they like to attract electrons? What do you think? Where does magnesium sit on the periodic table? More towards the left or more towards the right?
Left.
More towards the left, right? It's not close to fluorine. It's closer over on this side, right? So are they going to like to give up their electron? Yeah, they're going to want to give up their electrons. Metals like to give up their electrons. That's why they're electrically conductive, right? So if this doesn't like to take a lot of electrons, it's going to be positive. That means the carbon is going to be negative. These things behave like the R group with a negative charge. That's how they behave. They behave as carbanions. Okay? And so they're very strong bases, and they can do addition chemistry to carbonyls very, very easily. X can be any halogen except fluorine. It can be chlorine, bromine, or iodine. Doesn't matter. They all behave more or less the same. Okay? You all need to know a little bit about how Grignards are made. It's actually a very easy reaction to do. I don't think you all are going to do it in the lab. It's unfortunate. Because I can tell each and every one by how well you do a Grignard reaction, how well your skills are. It's the easiest way to determine a chemist's skills. If they can get a Grignard reaction to work, they're usually a pretty good practical chemist in the lab. If they struggle with it, they probably need to find another form of employment. Okay? And the reason is because you're forming strong bases, they like to react with the moisture in the air, and they like to react with some solvents that you might not have intended to get into the reaction. So if you're very careful, very meticulous, and you can make Grignard reagents, usually that means you've got really good lab technique. Okay? The Grignard reaction to make Grignard reagents, again, though, is on paper very simple. You simply take either, in this case, at the first one, we're taking an alkyl bromide. This is 1-bromobutane. You put it in diethyl ether solvent, and you have to make sure that the solvent's dry. And then you add magnesium to that, magnesium turnings. Magnesium is a metal. It does not dissolve. And you start to stir it. You make sure that your reaction is under an inert atmosphere, so there's no oxygen in there. You make sure there's no moisture in there. And you start to boil it. And at some point, it starts to look like the metal is dissolving. Okay? Well, that's weird, right? I mean, the metal doesn't really dissolve. It's reacting, and it forms the Grignard reagent. And so what's happening is the magnesium inserts itself in between the carbon and the halogen. And we're not going to talk about the mechanism for that happening. It's pretty complicated. But it is cool that we can break that carbon-halogen bond and make a carbon-metal bond, which is really nice. Okay? And you can do that for sp3 hybridized stuff. You can do it for sp2 hybridized stuff. You can make these Grignard reagents pretty easily, or pretty straightforwardly. Okay? And since they are strong bases, they will react with water, they will react with air, they will react with all kinds of things. They are not particularly flammable. They're fairly safe to work with, as long as you keep moisture and air away from them. That's not the case for some other organometallic reagents. If you were to take my 256 class, you would learn about another group called organolithiums that are highly flammable. And we never have an undergraduate student make those because people have died making them.
Are those ones that catch flame in oxygen?
They do. So, especially some of them more so than others. But you can take them, put it in a syringe, and squirt it out, and it'll be a green flame. They become a flamethrower. But unfortunately, a young lady in California several years ago, she might have been I can't remember if she was a PhD student or a postdoc, but she was a PhD student, and she wasn't paying attention, and she pulled the syringe out wrong, and it got all over, and it burst into flames, and she didn't make it. It was a sad thing. So again, these things like to react with water or any kind of acid, really. Okay, so you got to be careful when you use these. So again, the pKa of a Grignard reagent is somewhere around 35 or 40. It reacts with water, which has a pK of around 16. And so you take a strong base and you actually get a weaker base. So these reactions go to completion quite easily. That limits what you can use Grignard reagents with. If your molecule that you're trying to react the Grignard reagent with has any kind of OHs, NHs, or SHs, the chemistry will not work. Okay, and so chemists have to spend a lot of time trying to figure out how to make their chemistry work. So anything like that, you got to make sure isn't in the molecule when you are reacting it with a Grignard reagent. Okay? So here's an example of taking a Grignard reagent and reacting it with an aldehyde, in this case formaldehyde. So here we have CH3, CH2, MgBr, they're using the bromide, and they're going to react it with formaldehyde. Okay? Anytime I see a Grignard reagent, this is how I think about it when I'm working on paper. That's how I think about it. It is not that way. It doesn't really exist that way, but this is how it behaves. This is a carbon with a negative charge. It's a good nucleophile. That nucleophile attacks the carbon of the carbonyl and breaks that weak pi bond. And that's what we make in the middle, right? This is an alkoxide. Now all we do is we dump this over a little bit of dilute acid, usually over ice. And that's the organic product that we get. What is that organic product? What's the functional group? It's a hydroxyl group, and we call that is an alcohol. So what did we just do? We converted an aldehyde into a alcohol. How did we make alcohols before in this class? Hydration of what? You're right, hydration. Hydration of what? What did we hydrate? What did we add water to?
Alkenes.
Technically, we can do that with hydroxide through an SN2 reaction, but that's not hydration technically. So yeah, we learned how to make alcohols that way. But we learned how to make alcohols by adding water across a carbon-carbon double bond. Right? Remember, we could do that two ways. We can make more carbon alcohols. Here's another way. I can take a carbonyl containing compound and I can make alcohols. So I can take formaldehyde and a Grignard reagent and I can make an alcohol. What kind of alcohol is that? Primary, secondary, or tertiary? Primary. That is a primary alcohol. That carbon that contains the OH is only bound to one other carbon. Okay? I think some of you were thinking those were carbons. Those aren't. Right? So, yeah, we can make primary carbon, or primary alcohol. So if I want to make a primary alcohol, I can take a Grignard and formaldehyde.
There's supposed to be a C on that H3 at the end.
Oh, yep.
That is supposed to be about the
Yep, it is. Good catch. Here's an example of where we take a Grignard reagent, react it with an aldehyde that's not formaldehyde. It's already got a carbon bond to it. We're going to make another carbon bond, and now we're going to make a secondary alcohol. So I can take a Grignard and an aldehyde, and I can make a secondary alcohol. What do you think I would get if I took a Grignard reagent and a ketone? I'll get a tertiary alcohol. So you can make primary alcohols with formaldehyde, you can make secondary alcohols with aldehydes, you can make tertiary alcohols with ketones. Okay? Very important set of reactions here. We do this all the time in a real organic lab, because I know I can take alcohols and do other things. But what's the real important thing here? Why is it that this deserved a Nobel Prize, especially in 1912?
Bonding the carbon with a metal.
That's part of it, but in terms of their use, what was important about it? It was one of the first examples of a synthesized carbon, so I'm not disagreeing with you. What's the important thing that we're doing here? Is it making the alcohol that's important? No. What's important? What's important is I'm making a bond between two carbons. That's the most difficult thing to do in organic chemistry, is to make a bond between two carbons. More Nobel Prizes have been awarded for figuring out how you can make a bond between two carbons than any other thing has ever gotten a Nobel Prize for. You think about it, we're only given so much stuff from crude oil to work with. And we have to figure out how to connect those carbons together. And there really is only about 6 ways to do it, 7 ways. And every one of them has won a Nobel Prize. Okay? Or somebody that was involved in those has won a Nobel Prize, I should say. Nature does this so easy, and it's the toughest thing for us to do. Mother Nature's figured it out. We've kind of figured it out, but she's still better than we are at it, okay? And so this is a big deal, being able to make a carbon-carbon bond, okay? So there's the example of making a tertiary alcohol, right? You've figured that out, okay? So in the last couple of minutes that we have, I want you to work this problem in your groups. I want you to figure out how to make that alcohol.
I found this on the web.
Yeah, you do. How to make that alcohol. You have to use Grignard, but you can pick whatever you want. I'm not going to give you anything other than the fact that you have to use a Grignard. problem says by 3 different routes, you only have to find one for yourself. Pleasure. All right, I want y'all to work on this problem over the weekend. We'll pick up with this on Tuesday, but we're generating a tertiary alcohol. And I told you how to use a Grignard reagent. So what does that mean your other function group has to be? A ketone. So that must mean if there's 3 different routes, you need 3 different ketones and 3 different Grignard reagents. So think about that, okay? Try to come up with all 3. And we'll start with that on Tuesday. Have a great weekend, and I will see you all later.